Hi guys, so I'm going to go over the study guide that covers topics D01 through D04. I'm going to kind of go over some of the objectives of each lesson and then some of the practice problems. So let's start with D01. So D01 kind of goes over free body diagrams, as we kind of talked about before. Free body diagrams are basically diagrams that use arrows to define force, kind of like vectors. With each one, you should have a value. So for example, I'll put 5 newtons and 4 newtons. And then you should be able, using these diagrams, to draw net forces. Net force um, is going to be the sum of all the forces added. If it moves in the opposite direction of this force, so for example, this is 5 and this is 4, when you calculate them together, it should be 5 minus 4 to get a net force of 1 newtons to the right. That's something that we've discussed in class, and I will make a video kind of going over free body diagrams later on. But you should be able to define how balanced and unbalanced forces work on an object. So for example, since I have an unbalanced force right here, and I have a net force of 1 Newton, that my object will move to the right. You should also be able to say, if I have balanced forces, so if this is 2 and that's 2, that my net force will be 0, which means that I will have no movement on my object. Again, you should be able to draw free body diagrams illustrating all of the forces like I've shown right here. This also encompasses forces that are sliding up blocks. So if I have a block like this, you should be able to draw force of gravity, the force normal, and then the force of friction acting on the object. We've been over this in class as well, and again, I will make another video going over this. You should be able to determine the net force on a free body diagram and give the description of each one. So let's take a look at some of our practice problems. So for our first practice problem, 4 objects are each acted on by 2 forces as shown. Which object is at equilibrium? So as we kind of talked about before, equilibrium is basically going to equal 0 net force. Basically what that means is your object, when it's at equilibrium, will have no unbalanced forces. All the forces should add up to 0. So let's take a look at A. I have 1 Newton to the top and 2 newtons to the bottom, which means I have an unbalanced force, which means my net force will be down by 1 Newton. With B, I have 2 newtons going up and 2 newtons going down. So these forces are balanced, and that should account for a 0 Newton net force. So my answer for this question will actually be B. The reason it would not be C is because C has 3 newtons up, 2 newtons down, and so my net force would be 1 Newton up. The reason it cannot be 4 is because even though it has 4 and 4, the forces are not in the same direction. So what would actually happen with this object is it would get pulled up in that direction and pulled down this direction, and eventually lead to it looking more like this because it would straighten up and down. So because the forces are not on the same sides, they're technically not going to be balanced forces. So balanced forces need to be on the same point. So they need to be on the same point. Same point and magnitude. All right. So number 2, the diagram shows only 3 forces acting on an object. We have 3 newtons acting to the right, 2 newtons acting to the right, and then 5 acting to the left. What is the resulting force? The resulting force, so let me write that down. Resulting force is going to also be equal to net force. They're the same thing. What's the result is the same thing as saying what's the total force acting on it. So if I take a look at this, if I take both these forces are acting to the right of the object. So what I can do, since they're on the same side of the object, I can actually add these two together. So my total net force should be 5 newtons working to the right, and then I have 5 newtons working to the left. So if I take this 5 and 5, I'm going to have a net force of 0 newtons. So automatically I can choose A as my answer. But if I have 5 newtons to the left, my object would actually start moving, which means that these forces would have to be 0 on the left-hand side, and they're not. I have a 3 and a 2. 5 newtons to the right would basically indicate that this would be 10, which isn't true either. So my left-hand side would have to be 10 newtons to make it move 5 newtons to the right. And then 10 newtons towards the right would indicate that this would be 15 newtons. So just basically balancing all the equations and equaling them out and finding net force. All right. So let's move on to part 3, or problem 3, my bad. So the diagrams show 4 identical objects. Each object is acted on by only 3 forces shown. Which object accelerates to the right with the smallest acceleration? All right, so if we look at this, we're looking for something that has a small acceleration. Um, and again, forces do not cause movement, acceleration does. So we're looking for which one's going to start the movement to the right-hand side with the smallest acceleration. So if we look at A, we have, since they're both on the same side of the object, these two would be a 50 Newton to the left and a 10 Newton to the right. So technically I would have, my net force would be 40 Newtons to the left. So I knew that one is the wrong answer with A. B, okay, I have 10 and 20, so I have a total of 30 Newtons to the right, 30 Newtons to the left, so I have a net force of 0. C, I have 10 and 30 to the right and 20 to the left. So if I add these two together, I have 40 newtons. This one is 20. So my overall force is 20 newtons to the right. D. So this one's still, as you guys can see with C, it actually accelerates to the right. So this is still one of my options. I'm just trying to see if it has the smallest acceleration. So we've already met one checkpoint with that. It's to the right. Now we just need to make sure it's the smallest out of all of our options. So the last one, D, is 10 plus 20 plus 30. So if you guys look at that, that should be 60 newtons. So my net force is 60 newtons to the right. So it does check off that box that it is to the right, but it's not the smallest acceleration. That goes to option C. All right. 4. Which combination of forces produces a resulting force acting towards the right? So all our problems today have actually been to the right-hand side. Be prepared to be able to find out ones to the left. It's the same principle. But if we take a look for option A, we have 10 newtons to the left, and we have 7 newtons total because we add these two together. So our total to the right is 7 newtons. So this will actually accelerate with a net force. I'm going to put net is equal to 3 newtons to the left. So option A is out. Option B, we have 5, and if you add these two together, this should be 7 newtons. So we have 7 newtons moving that way, 5 newtons moving that way. Our net is going to be 2 newtons to the right. So if we look, resulting force acting to the right, B is actually going to be our correct answer. Let's go over the other ones just to make sure. With C, this would be 10. This would be 10, so our net force would be 0. D, I have 5 and 3, and then 7 on this side. So this is 8 newtons and 7, so I'd actually have a net force of 1 newton to the left. So hopefully that helps with D01. These are just basically being able to draw free body diagrams, looking at them, and then writing down the forces that act on each other. These problems are not very difficult as long as you know what force should be what. All right, with D02, you want to be able to define how acceleration of an object is based on this formula. So force equals mass times acceleration. You want to recognize the effects of forces on a distance versus time graph. That's going to be a lab that we cover this week as well. But basically, you're looking to see how forces are going to affect a distance versus time graph. And basically, as a force increases the velocity or changes the acceleration of something, you should see a change in velocity, which will cause a change in distance over time. The last one, describe the relationship between friction and motion. You want to talk about how friction affects motion. So if I push a block like so, if I apply a force this way and friction acts on it, how does friction affect the motion or the acceleration of an object? So what would actually happen is the friction force would decrease the force acting on it, right? So if this force went down, which means my acceleration would also go down as well. So this formula, F equals ma, is a huge part of Newton's second law, and it basically talks about so for example, if I have force, if my force increases and my mass stays the same, then my acceleration should also increase. If, for example, my force or my mass increases, then my force must increase, which then in turn increases or actually your acceleration would decrease a little bit due to the mass. So it's kind of a weird game that it plays. You just have to make sure that you can take values of F equals ma and apply it back into the formula. We've also used this before. So force is equal to mass times acceleration. This triangle is one that you're very familiar with the velocity equation. It's basically the same principles as that. So if you wanted to find mass, it's force divided by acceleration. All right, let's take a look at some of these practice problems, see if we can answer some of them. So a car produces a driving force of 5,000 newtons on the car with a resistive force R. So also acts on the car. The car has a mass of 800 kilograms and an acceleration of 1 meter per second. What is the value of R? So what we're looking for is we're actually looking for R, right? How we figure that out is this equation right here, F equals ma, is actually net force. So this is going to be your net force equation. So using this formula, it's not exactly going to find R. What I have to do first is find my net force acting on the object. So if I look, my mass is 800. My acceleration is 1. So then my net force is going to be 800 newtons. So what it's saying is option A looks like it would be correct, but that's going to try to throw you off. Because what's going to happen is if my force on the object is 5,000, I have to have a resistive force, and then the net force has to be 800. So what I'd have to do to find the R force is because this, say, net force will equal a force applied minus force of resistance or force of friction. So if I take that same idea, I have 800 newtons equals 5,000 minus R. So I take 5,000 to this, get rid of it, minus this by 5,000. And then my answer should be negative 4200 newtons, negative R. So then my resistive force would actually be positive 4,200. So my answer should be B. That's how you solve these. It's basically simple algebra. Um, again, you probably could have solved it a little faster than I did in this example. Basically, all you have to do is figure out your net force. From there, you can take your net force and plug it into a equation to figure out what your resistive force would be. All right, let's take a look at problem 2. A parachutist is falling down at terminal velocity. So something at terminal velocity, when it hits terminal velocity, basically that means the force of air resistance is equal to the force of gravity pulling on it. So these two forces would be equal. Okay. Without the parachute open, she now opens her parachute. So as the parachutist falls, right? So here's a little parachutist. As they fall, she's going to open her parachute. So I'll draw her little parachute right now. What is the direction of her motion? So one of the things is with a parachute, it always is going to go downwards. So if we look at the direction of motion, it's always going to go down. It's not going to go up. At no time will someone falling out of a plane all of a sudden start flying upwards. So we can cross off C and D. The next part we have to take into consideration is the direction of acceleration. So again, when I open the parachute, her initial movement isn't going to be downwards, because what's going to happen is she's going to have a gust of air resistance. And that gust of air resistance would actually cause motion, right? So when you pull a parachute, if you think about it, the parachute doesn't open and you keep falling down. What will happen is you open it and it initially kind of brings you up a little bit. But your general motion is still down. What happens is that acceleration, what you feel is an acceleration of movement upwards. So what you're actually going to have is you're going to have a upwards acceleration at that point. All right. 3. The diagram shows a satellite that is moving at a uniform rate in a circular orbit around Earth. So it's moving at a uniform rate and it's in a circular motion. So one of the things with the satellites is it's asking what statement best describes the motion of the satellite. If we talk about just acceleration. To kind of step back. So acceleration is a change in velocity. Velocity is distance and speed. Or speed with distance. So if my speed stays the same, but my direction, my bad, not distance, direction. So if my direction changes, right, then I would technically have a change in velocity, which means I have change in acceleration. So thinking of this same concept. So with acceleration, if I change my velocity, I change my acceleration as well. So, or it would be accelerating. So A, it is accelerating because its speed is changing. Well, it says right here, it travels at a uniform rate. So is my speed changing? No. So that doesn't cause the acceleration. B, it's accelerating because its velocity is changing. That's an option because technically velocity is speed with direction. So that could be a good choice. C, it is not accelerating, but the speed is changing. That's not true as well. It says uniform rate. And then it is not accelerating, but its velocity is changing. That cannot be true because what we know about velocity is acceleration is change in velocity. So if the velocity is changing, it is accelerating. So D cannot be true. So the only option left is B, which means that it is accelerating because its velocity is changing. So its direction's changing, which means its velocity is changing, which in turn causes an acceleration. All right. D03. So this one you're going to determine when friction occurs. You should be able to identify the effects of friction on an object and an object's motion. These are basically finding friction problems. There will be a lot of calculations within these ones. Again, it's not very difficult as long as you know how to apply the formula. That formula is basically going to put it right here. So the force of friction is equal to the coefficient of friction and that varies with the surface that you're on. And then it's also going to be times your force of normal. Cool? So let's just try one for an example. So what is the best estimate of the magnitude of the box's acceleration? So we're going to look at this. A 3 kilogram box is at rest on a table with the static friction coefficient being that. Between the box and the table, there is 0.4 of kinetic friction coefficient is 0.10. Then a 20 Newton horizontal force is applied to the box. All right, so sorry about that. Basically, when you're looking at these kind of problems, you have your mass, you have your static friction. So there's two differences too. You should know is static means staying still, while kinetic means moving slash sliding. So with friction, we have two types of friction. We have static, which is staying still. So there's a friction when two objects are just touching each other, and there's a kinetic friction when things are moving or sliding. It's up to you to kind of determine which coefficient you use in which scenario. So, for example, in this one, you have a 3 kilogram box at rest on the table. The static friction coefficient is 0.4 and the kinetic coefficient is 0.10. There is a 20 Newton horizontal force applied to this box. So if I draw here, I have force normal, force of gravity, a 20 Newton force applied, and then we're looking for this resistive friction force. So all I have to do is I know that I'm going to use this 0.10 in my equation. So to find my friction force, I have to use 0.01 and then I have to use my force normal. And so my force normal is actually going to be 3 kilograms times 10 meters per second squared, which would actually equal my force normal will be 30 newtons down. So I go 30 newtons down. And so if I look, my force of friction will actually be 10% of 30, just so you guys see it on the calculator. is you go 30 times 0.1, so it should be 3. So if we go back here, my force of friction should be 3 newtons. Cool? And that one too, if you wanted to, you could write -3. That indicates that it's minusing from the 20 as well, or moving to the left. But if you just left it as 3 newtons, that would be correct as well. All right, let's move on to problem 2. So problem 2, a 4-kilogram box is at rest on a table. The static friction coefficient is 0.3, and the kinetic coefficient is 0.1. There's a 25 Newton horizontal force applied to the box. What is the best magnitude of the box's acceleration? Oh, actually, let's go back to this problem down here. I didn't find the force of acceleration. So my force is going to be equal to mass times acceleration. So my overall net force, if I have 3 newtons back and 20 newtons forward, it's actually going to be 17 newtons total. My mass is 3, and my acceleration is what I'm looking for. So I'd actually just take 17 divided by 3. So let's clear this. 17 divided by 3. It's going to be 5.67. That's what I'm going to put as my answer. So I'm going to go here. Acceleration equals 5.67 meters per second squared. Cool. Now let's move back to the next problem. Sorry about that. So if we look back at this problem, we have a 25 Newton force applied. What is the best estimate of the box's acceleration? So we have a box. Well, that's a circle, but still in our world, it will be a box. It's moving at 25 Newton horizontal force. We're looking for our friction force. So we're still using this equation. Force of friction is equal to the coefficient times the force normal. Our force normal is equal to mass times gravity. So in our case, we have a 4-kilogram box times 10 meters per second squared. So our force of normal should be 40 newtons. So we're looking for the force of friction. Our coefficient that we're going to use is, since it is sliding, it does have a 25 Newton horizontal force. We're not going to use static friction. We're actually going to use kinetic coefficient. So we should use, since it's moving, we're going to use this coefficient. So we should use 0.1 times 40. And I can tell you right off the bat, 10% of 40 will be 4 newtons. So our friction force is 4 newtons. So then our total force equals mass times acceleration. If we have 4 returning from 25, our total force will be 21 newtons. Our mass will be 4, and our acceleration is what we're looking for. So then I go back over here. I go 21 divided by 4 equals 5.25. Back here, my acceleration is 5.25 meters per second squared. And that's my overall my overall acceleration, and then this is my friction force. So on these equations, you're most likely going to see problems that relate to finding the friction force of an object and then using the acceleration. I might make them a little easier for you on the test as well. I might make them so that it just gives you one coefficient. So all you really have to do is plug in one coefficient instead of deciding between the two. But if you are asked to decide between the two, you should know the difference between static and kinetic. All right, last topic, D04. So you're going to calculate gravitational attraction between two objects. You need to differentiate between weight and mass. So key thing with weight and mass is weight is a force of mass times gravity, whereas mass is actually amount of space you take up. So there's a little bit of a difference, right? And then gravitational attraction is basically figuring out what's the force between two objects with a certain distance. The equation that you're going to use for that, as I'll put it in the comments, is your force of gravity will be equal to your gravitational constant, your mass 1, mass 2, and then you will go your R2 or D2. It's the same exact thing. So what we're going to have here is two spherical objects have masses of 1.5 times 10 to the fifth kilogram and then 8.5 times 10 to the second kilogram. Their centers are separated by a distance of 200 or 2,500 meters. Find the gravitational attraction between them. So what's actually going to happen is you are going to go to here. We have our gravitational constant will be 6.673 times 10 to the negative 11. That's our gravitational constant always. So whenever you're looking for this big G, you're actually just looking for this constant. Your first mass will be 1.5 times 10 to the fifth. Then it should be 8.5 times 10 to the Cool. And so what you're looking for is the force of gravitational attraction between them. So what we need to do is we need to start plugging all of this into a calculator. So I should have 6.673 times 10. And then I need to go to this, and I'm going to go 11 negative. So that should be the first constant. The second one, I need to go back here, will be 1.5 times 10 to the fifth. So I'm actually going to times this by 1.5 times 10 to the fifth. All right, and then I'm going to times all of that by my third value, which would be 8.5 times 10 to the 2. So I'm going to go 8.5 times 10 to the 2. All right, and that should be my answer for the value on top is 8.5. I'm going to go here, and then I have 8.5 divided by 2,500 squared. So let's do that. So we have 2,500 squared, right? So our value will actually be 1, 2, 3, 4, 5, 6. 6.25 times 10 to the 6th. So let's go here. And we had 8.5 divided by 6.25 times 10 to the 6th. And our answer should be 1, 2, 3, 4, 5, 6. So it's 1.36 times 10 to the negative 6 should be my answer. So my answer should be 1.36 times 10 to the negative 6. And that should be in newtons, and that will be my final answer. So again, these attractions are going to be really, really small. So if you think about it, the gravitational pull between two objects is not going to be very high unless you're considering planets. So something that has a really, really high mass, you would have huge gravitational pull, but you wouldn't really have a lot of gravitational pull between two regular sized objects. All right, let's take a look at this one. Two spherical objects have equal masses and experience a gravitational force of 25 newtons towards one another. Their centers are 36 centimeters apart. Determine each of their masses. So we have the same formula from up here. We'll use that same one. So we have 25 newtons is equal to gravitational mass 1, mass 2, all over r squared. So the distance apart, we have that as well. So let's erase this and plug that in. So we have 36 squared. So 36 squared is 1,296. 1,296. And so we're going to take that and get rid of it and put it on this side. So we can cross these out. So then we have 1,296 times 25. So 32,400. I'm going to come back here and we're going to erase this because what we've done is multiply them together. Then we have 32,000, what was it, 400. And then I'm going to erase this to kind of clean it up. So we cross cancel these. And so what we have left is this. And then we know what G is. We know that G is going to be 6.673 times 10 to the negative 11th because it always is. So we're actually going to divide G out and then divide this by G, which is 6.673 times 10 to the negative 11th, right? And so then we should be able to cross these out, which means I can get rid of this. And then, so I'm going to go here, divide that by 6.673 times 10 to the negative 11th. And my answer should be my decimal points right here. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm going to say 4.86 times 10 to the 14th. So if I go here, my answer should be 4.86 times 10 to the 15th equal mass 1 times mass 2. And so basically, mass 1 times mass 2 are equal to m. So then I just have to take this and divide that whole number by 2. I go back here and I divide these by 2. I could see that this will technically be 2.43. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it should be 2.43 times 10 to the 14. So my answer should be 2.43 times 10 to the 14. So obviously, as you guys can see, the masses of these are huge. They're huge masses, and they're not that far apart. So to have a gravitational force of just 25 newtons, which is really strong, you would have to have these huge masses. These are probably the size of small planets, actually, and that's how you're getting such a huge force. So 25 newtons is actually a substantial force. So to get something like that, you'd have to have very large objects sitting next to each other. So these masses are obviously going to be really, really big to match that. All right, last one. Let's get back here. So our last one. Two spherical objects have masses of 6.3 times 10 to the third kilogram and 3.5 times 10 to the fourth kilogram. The gravitational attraction between them is 6.5 times 10 to the negative 3. How far apart are their centers? So we're still going to use this one if G equals G M1 M2 and R2. So what we'd actually have to do is with simple algebra, if we're looking for distance, we're actually going to have to flip these two. So it should be R2 is equal to G M1 M2 and then F. And then what we have to do is we have to square root this to cross out this and this. And then we have to square root that whole thing. So basically, to find just the distance between two objects, we have to find the square root of G times M divided by F. To kind of show you that is, I already know what my G is. It's going to be 6.673 times 10 to the negative 11. I know that my first mass is 6.3 times 10 to the third. And then I also know that my second mass is 3.5 times 10 to the fourth. So let's just start with there and solve all that so we can get our standard number on top. So we're going to, it should be 6.673 times 10 to the negative 11th. And then we have 6.3 times 10 to the third. So it should be times 6.3 times 10 to the third. And then we're going to do one more where it should be 3.5 times 10 to the fourth. So then we're going to times that by 3.5 times 10 to the fourth. So our final answer is it's 1.47 times 10 to the negative 2. So this should be 1.47 times 10 to the negative 2. And then we divide it by our FG. So our FG, our force of gravity, the attraction between them, 6.5 times 10 to the negative third. So we're going to divide that 6.5 times 10 to the negative third. And our answer is 2.26. So our answer is going to be 2.26. And then what we have to do is we actually have to take this and square root it. So it should just be 1.5 is our answer. So once you square root this, our final answer is 1.5 meters apart. So again, it seems like a lot of work, and it is a lot of work, but as long as you know your values and just plug them into the equation, you should really have no issue with these. All right. So if there's any question on these, please feel free to come into tutoring. I will post up all these notes online as well to kind of help you guys review along with this video, and hopefully that helps as well. If you're still having trouble, again, come into tutoring, come in to see me at lunch after school. But hopefully this helps, and take the modules and go through the modules, review with them. They are good checks, and I will also post up individual videos for each topic as well. All right, you guys, have a good night.